All right, let's get started with our second problem of the day. This one is LeetCode number 62, unique paths. There is a robot on an M by N grid. The robot is initially located on the top left corner. The robot tries to move down to the bottom right corner. The robot can move either only down or right at any point in time. Given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. And tests are generated so that the answer will be less than or equal to 2 times 10 to the 9. And the constraint is that m is greater than or equal to 1, and n is less than or equal to 100. So given that the number is less than or equal to 100, I suspect that this algorithm will not necessarily be quite fast. Considering that this says generate the number of possible unique paths, I wonder if this could be rephrased as generate all possible unique paths to the finish line. And the idea, let me think about this a little bit. So m represents, in this case, a number of rows. N is the columns. For each cell that the robot can traverse, it can take one of two choices. It can either go right or it could go down, except for the edges, specifically on the right edge and bottom edge, where it can only move in one direction. So there's no exception there. So what could we do? If we're talking about this from a backtracking perspective, in terms of generating all possible unique paths, well, our constraint is that the robot must must travel to a valid square, where valid is m is less than, or the row is less than m, and the column is less than n. Because assuming that we start at 0, 0, then 1, 2, 3, 4, 5, 6 is the maximum, and n is 7. So row is less than m, column is less than n. Similar story for the rows, by the way. And we can sort of check, we can, I guess, explore on each possible iteration the number or the possibilities of that particular cell. And then increment on the number of possibilities, and return when we reach the bottom cell. So I think that's possible, one possible approach. And this would be an O of 2 to the n, pretty much, runtime algorithm. And the reason why it's 2 to the n is because really at each cell we have 2 forks that we could go. And the number of possibilities at each cell, I think, is relatively, from what I'm thinking about right now, they seem relatively unique. Given that the n is less than 100, but m could be a pretty large number. The only restriction is that m is at least 1, but there's no upper restriction on how large m could be. Well, we can say that in the case of in terms of m is equal to 1, we can just return 1. Because in that case, you can only move the robot if there is only one row, then it doesn't matter how many columns there are. You just move to the right. That's the only unique path that there is. Because you always start on 0, 0. And I think if n is equal to 1, that is also the case. Because if there is only one column, then it doesn't matter how many rows there are. You only have one path, and that's down. Fair enough. Oh, okay, so m and n are bounded by, sorry, I was looking at the constraints completely wrong. It's m, it's like this. It's 1 is less than or equal to m, n less than or equal to 100. So m and n are bounded by 1 and 100. So at the most, it is a 100 by 100 grid. And if there is a 100 by 100 grid, then that's a lot of cells, actually. And if there are that many cells, because 100 times 100, that's what, 10,000 cells? In that case, if there are 10,000 cells, also the runtime is incorrect because we're only considering n. But 2 to the m by n, that's an insane amount if we're doing 10,000. Yeah, that would be heat death of the universe type length. So there must be a better way. What if we start at the corners? At the other corner. What I mean by that is that we know that if we had a cell like this, and we had that there, we know that there's only one path at each of these spots on the edges. There's no roots there. We know that there are 2 here. We could either go down and to the right, or right and then down. Is there anything that we could do for the rest of these? So what I'm imagining is that if m and n are 100, that's 10,000 cells. So 2 to the m by n answer is unrealistic. And therefore there must be a better solution. The first solution that I've thought of is potentially using dynamic programming. Because it seems that dynamic programming is a fairly common solution in the case where you have a exponential blowup where you must solve the problem in non-exponential time. So we know that the edges carry a value of 1, but we don't know much else. But what if we think about this in a different way? Let's say that, So if we know that the edges carry a value of 1, and this value here is for sure 2, then perhaps a subproblem that exists is that the solution of m and n of unique paths is equal to the unique paths of m minus 1, n minus 1, plus 2. We know that the edges will always have 1, and we know that therefore that this bottom left solution, or this bottom right solution, right adjacent or diagonal on the top left to our solution, will have a value of 2. You can either go right and down or right. Interesting. And in that case, what is our base case? Well, is our base case just this? If m is equal to 1 or n is equal to 1, return 1. Okay. But how do we represent this? If we're going with a dynamic programming solution, then there must be a representation of this within some sort of table in order to speed this up. Assuming that we're doing perhaps a bottom-up recursion. Well, if we had 0, 1, 2, 3, we'll have each of these here. And we'll have each of these here. So these represent the columns. This represents the row. Well, in a 0 by 0 grid, there are 0 paths. And actually, this entire thing is 0 for both of these situations. Because if one of the rows or the columns is 0, then of course there is no path. And of course we know that if one of them is 1, then there is only one path. What about 2? Well, for 2, we know that the the number of pads in a 2 by 2 grid is equal to the number of pads in a 1 by 1 grid plus 2. In this case, it would actually be 3, but the real answer I think that we're looking for is 2, because if we had a 2 by 2 grid, robot stands here, ending is here, you can only go right and down or right. So actually this 1 by 1 grid will also represent 0 pads, or should, because there is no possibility for it to actually work that way, right? At least, I think. What happens? Actually, let's just do a return 0. And let's do a 1 by 1. And let's just do a sanity check to make sure that there are 0 pads in a 1 by 1. Okay, no, there is technically 1 path in a 1 by 1. Interesting. We'll go with it. We'll go with it. What about a 3 by 2? Well, a 3 by 2, in this case we can go 3 ways. We can go right, down, down. Or actually, no, this is sort of the opposite, right? We can go, oh no, so this is 2 by 3. So two rows, 3 columns, yep. So we can go right, right, down. We can go down, right, right. We can go right, down, right. So right, right, down, right, and down, right, right. And those are the 3 ways. In that case, is the number of solutions that exist equal to, rather than the corner plus 2? Well, if we reduce it to this, so this 2 by 2, we have 2 ways. And if we had a 1 by 3, then that's 1 way. So therefore there are 3 ways. So do we actually, instead of taking the corner, do we add the number of items from m-1 and n-1 recursions? Well, that actually does make sense. Given that if we are talking about the O of 2 to the m by n solution, we know that we have a choice between going right or down, right? So in that case, it does make sense that our solution actually is made up of the solution of going right, of m-1 and the solution of n-1 together. So assuming that is the case, then the number of solutions for a 4 by 2 is 4, then 5, then 6, then 7. In this case, it's 3, then 6, then 10, then 15, then 21, and 28. I see. Looks like we're getting somewhere, actually. Okay, so this might actually be the case. Okay. Interesting. It does seem to work for both of the example cases that we've done. So for a 3 by 2 where m is 3 and this is 2, there are indeed 3 ways. So this might actually be it. So I think this is actually a decent enough approach that I would go ahead and start coding this. Of course, this will take, rather than O of 2 to the m by n time, This will take O of m by n time by itself with the same amount of space. So let's go ahead and do that. Technically, we could reduce the space by one row and one column, but that won't really affect our asymptotic complexity. That might be something that you might consider for competitive programming, but I think in this case, we're fine with just having it be zero indexed as usual. So let's get started. We'll do our dynamic programming grid as an array of int array of size m, where we do an int array here of size n, and we'll just initialize them all to 0. Okay. Then we can do dp for each indexed. This will be the rows. Row index and the row itself. And row for each indexed. Call index value. Well, we can say that if, or we can say when row index -1, or if row index is 0, we don't care about the 0 index, or call index is 0, we can just do nothing. Otherwise, if row index -1 is 0 and call index -1 is 0, or actually we want to do dp at row index -1 call index, and actually we can do row index is 1 or call index is 1. We want dp of row index call index to be equal to 1. Otherwise, we can do dp of call index -1 first row and then column, so row index then call index plus 1, plus dp of row index -1 call index -1, or no, not -1. And this will be dp of row index call index is equal to the sum of those. So if the row index is equal to 1, they're all 1s. If the column index is 1, then they're all 1s. Otherwise, they are the sum of all of them. And then we can just return dp at m and n. -1. Because 0 indexing. So if they're both 0s, then we initialize them to 0, so it doesn't matter. If either of them is 1, then we initialize it to 1. And we can actually do this. dp of row index call index is equal to, and so this should return an integer. And we can simplify this logic a little bit. So now this value will be equal to either 0 when they're both 0, 1 if either of them are 1. Otherwise, we take the row, one row up and one column up, and we add them. And then we just return at the end. Let's go ahead and run this code. Actually, if m is equal to 1 or n is equal to 1, return 1. Let's go ahead and run those solutions. Interesting. Didn't quite get to where we wanted, actually. Let's do a print line then. We'll do row index call index is dp row index call index. Right, so 1 1 1 2, right? Actually, let's just shrink this down to the 3 and 7 case. Okay, so all the ones, all the row ones got 1. And then we go to row 2. 2 and 6. Why did we only get to there? M is 3, N is 7. But we only made it to this? We only made a 2 by 6? Why is that the case? It should be of size 3, right? This isn't... This is really odd. Let me print dp.size rows columns dp at m dot size. That's fine. Why is interesting? Should be a 3 by 7. It is a 3 by 7. But this for each index only goes up to there. It only goes up to 2 by 6. Does it really just not go over all of them? Interesting. It goes up to column row 0, row 1, row 2. No, never mind. I'm stupid. No, it needs to be m by 1 and n by n plus 1 because we need an additional row. We need an additional row because everything is 0 indexed. God damn it. This is... Well, that was embarrassing. You need an extra row and column because of 0 indexing. You buffoon. Let's throw in a submit and let's see how fast we can get this. Okay, cool. Good enough. Again, most people probably did the whole like, oh yeah, we'll just like one index this, and I mean, actually, would it be that hard to do that? Like, we could do this, right? And initialize them as ones. And we initialize this as 1. And then we do this. And this is m minus 1. This is n minus 1. Does this work? Like, just like some minor changes to one index them. Yeah, this works. Okay, cool. Okay, yep. Well, yeah. So in this case, we had a sort of backtracky type of problem where we were asked to essentially generate all valid paths, but in this case, we just wanted the number of paths. The first thing that came to my mind was a backtracking type solution. But of course, with a 100 by 100 grid, that's way too slow. So I think if you actually map it out as well, there are some overlapping points that you can consider. But generally, the solution is like, if backtracking is too slow, then you can consider dynamic programming. At least that's what I've seen so far, right? That was the case with that one problem, which was partition equal subset sum. Was that the one? I think that one I did. That one may have been a backtracking one. No, that one was dynamic programming. I remember now. Yeah. So yeah, so generally if backtracking is too slow by itself, then there are probably overlapping subproblems, and in that case you could probably approach this with a dynamic programming like solution. In this case, we kind of modeled this, and I think some people will say that this is like the O1 knapsack type approach, which I think it's pretty valid. It's pretty close to the O1 knapsack. Though I'm actually not that great at dynamic programming, all things considered, but yeah. In any case, I hope you learned something, and I will see you for the next problem.